We're continuing with our preliminary material, which again should be review from pre-algebra and algebra 1. Today we're going to be talking about radical expressions and rational exponents. So let's think back to if we were to evaluate expressions, bases raised to some power. So if I have b to the 0 power, we know that to equal 1 if and only if our base b does not equal 0, because that opens up a whole other world that we're not ready to talk about. So right now, we would say that any base, as long as it's not 0, if it's raised to the 0 power, that simplifies to 1. B to the first power is b squared in expanded form would be b times b, and b cubed would be b times b times b. So again, that exponent tells you how many times to repeat the base by multiplication. So if I let a squared equal b, if I want to know what a is, I could take the square root of both sides, and I would see that a equals the square root of b. Now, if I don't have what is known as a root index here, if I don't have a root index there, I know it to be 2. So if I wanted to write a, I could either write it in this notation to represent the square root of b, or this notation to represent the square root of b. And if I wanted to write b to some rational exponent power instead of as a radical expression, I would keep the base b. We know the exponent of b is 1, which becomes the numerator of the rational exponent, and the root index 2 becomes the denominator of the rational exponent. So to get our fractional exponent, to convert from radical form to a base raised to a rational exponent, you keep the base with its exponent becoming the numerator of the rational exponent, and the root index to become the denominator of the rational exponent. We have a radical symbol. We have what's inside the radical symbol known as the radicand. So in this case, A is the radicand. And as we first were introduced to this little bar over repeated numbers, that is known as the vinculum. So when n equals 2, we are talking about the square root of a, which again can be represented without the root index, and that is for a square root. Now, it is very helpful to know your perfect squares. So you should be able to complete this table at least up to 20 squared without using a calculator. These are numbers that you are going to need to have committed to memory to be able to work with problems in the future with ease without having to look up the values of these perfect squares. So again, if you don't know your perfect squares up to at least 20, 25 would be better, then you should commit these to memory. So you should be able to populate that table in no time. Now, if you are asked to estimate the value of a radical expression, in this case the square root of 27, I know my radicand, 27, is not a perfect square. So if I wanted to estimate that, let's say to the nearest tenth, well, I could estimate it by saying, all right, what two perfect squares does 27 fall between? And hopefully you would be able to say, oh, between the square root of 25 and the square root of 36. So 27 is in between those two perfect squares, 25 and 36. Now, if I take the square root of each of those, I know square root of 25 is 5. The square root of 36 is 6. 27 is closer to 5. So I would say it's a little bit more than 5. Now, if I put it in the calculator, I will get that it is approximately 5.2, but you should be able to estimate it. You should be able to say, oh, it's a little closer to 5, but more than 5. Now, what about the square root of 55? The square root of 55, well, 55 falls between what two perfect squares? Well, hopefully you can say 49 and 64. So what are the square roots of each of those? You should be able to say 7 and 8. And it is actually closer to 7. If I put it in the calculator, I will see if I want to round this to the nearest 10th place, it would be 7.4. Now, let's talk about properties of square roots. Properties of square roots. Well, let's say we're working with numbers a and b, where a is greater than or equal to 0, and b is greater than 0. The product property of square root says that if I take the square root of a product, so notice that the radicand is the product AB, I can split that into the square root of A times the square root of B. Similarly, if I'm given two different radical expressions and I'm taking the product of them, I can combine both of those radicands by multiplication, in this case, inside the radical expression, the radical symbol. So, keeping that in mind, sometimes it's easier to rework the problem by maybe factoring the radicand. So in this case, if I'm looking at the square root of 12, I can factor 12 as 4 times 3, and then I could see that 4 is the product of 2 times 2 times 3. And I could split this as the square root of 4, which is 2 times 2, is 2 times the square root of 3. Now, you can try the next additional examples, and then hopefully you can get the correct answer. So all I'm doing is factoring the radicand. Now, you want to try to choose perfect squares, if possible, and perfect squares that are the largest perfect squares. While there may be different factors, if you choose the largest perfect square, it makes the problem more easily simplified in fewer steps. Keeping in mind that taking the square root, you need 2 repeating numbers, so one comes out and the other one disappears. Now, can you write these as with rational exponents instead for kicks? Yeah, we could have written this, if we wanted to, as 72 to the 1/2 power, remember? Now, looking at the next example, I have the square root of 16, 4 times 4, times another 4, giving me 4 times the square root of 4, but then I can continue to factor the radicand 4. And then what do I do? Well, I'm going to take out that one of the 2's. And what do I do with those 2 numbers? Multiply them together. The next example I have from this one up here, I know that this is 36 times 2 times another 3. We said that was 6 times the square root of 2 times 3. There's nothing further I can simplify, so I'm going to multiply those 2 factors inside the radical, make that radicand just a 6. So 6 times the square root of 6. Now, a similar property holds for quotient of square roots. Again, I can have the square root of a quotient, and I can rewrite it by taking the square root of the numerator and the denominator. Or if I have the quotient of 2 square roots, I could combine those radicands and just have the square root of a quotient. And that actually works for any root index. Now, looking at this example, I see that 25 divided by 16 doesn't simplify nicely. They don't share a common factor. But I could split this square root of a quotient as the quotient of two square roots and simplify it this way. Or, in some instances, you might want to combine the radicands because they simplify nicely, allowing you to simplify further in fewer steps. An additional example which can be worked either way, I could split it and simplify it that way, or I could have just simplified from the get-go. See, sometimes it's easier to do it one way, sometimes it's easier to do it another. Now, if I want to simplify the expression of this form, keep in mind the root index, if we don't see it, is 2. If I wanted to rewrite this with a rational exponent, power to a power, keep in mind you keep the base, multiply the exponents. Notice how that simplifies. However, the square root of a squared does not always equal a. It depends what that a is. If a is positive or a is negative. So what we would really like to look at is this in terms of the absolute value of a. So in that case, if we have the absolute value of a, that's two cases. If a is positive or equal to 0, it equals a, so that's case 1. However, it equals negative a if a is less than 0. So we have two cases. And we'll look at absolute value in detail a little bit later. So when is the radicand in simplest form? When the root index is 2. Well, if no perfect squares appear under the radical, or, no radicals, radical expressions, are in the denominator. So the question is, when are you finished working the problem? When do you have your final answer in those two instances? Now, if b cubed equals c, then to solve for b, I would take the cube root of each side. And so b would equal the cube root of c. And notice that the root index is 3. I still have a exponent of 1 there, even though I don't see it. So if I wanted to rewrite the radical expression with a rational exponent, it would be c to the 1/3 power. So let's use our properties and see if we can simplify these. Square root of 32. I'm going to factor, trying to choose large perfect squares if possible. Then I'm going to use my product property of exponents, of square roots, and then I'm going to keep going. And I'm going to get 4 times the square root of 2. In the next case, I prefer to simplify by splitting that quotient into the square root of the numerator and denominator, separately evaluating the numerator and denominator to get the final answer. In this case, that's not a perfect square, so I prefer to combine those two radicands by multiplication, giving me 36. Now that's a perfect square, allowing me to simplify that easily. In the next example, I prefer to combine using the quotient property, giving me the square root of 100, which simplifies to 10 since it's a perfect square. And again, when I'm dealing with rational exponents, keep in mind that the exponent of the radicand, this is a very important rule that's going to be helpful, is the numerator. The denominator of the rational exponent is the root index. But most important to remember is that I can write this, well, keeping the root index as the root index, but I can either put the exponent on the inside or on the outside. So in other words, I could raise a to the m power first and then take the nth root, or I could take the nth root of a and then raise that final answer to the mth power. Sometimes it's easier to do this, sometimes it's easier to do this. Rule, it's going to make your life a lot easier. So, we said one of the things that conditions we have to satisfy to have a final answer dealing with radical expressions is that we cannot have a radical expression in the denominator. If we do, we have to address it. We have to rationalize the denominator so that we do not have a radical expression in the denominator. So let's talk about how to do that. In example 7, I see that my denominator is the square root of 7. Well, I know if I multiply a radical expression by itself, square root of 7 times the square root of 7, I get the square root of 49, which is just 7. So I could take this original expression, 3 times the square root of 5 over the square root of 7. And if I multiply both the numerator and denominator by the square root of 7, I mean, you're asking yourself, what am I multiplying the denominator by so that I no longer have a radical expression? Well, this is going to give me, in the numerator, 3 times the square root of 35 over the square root of 7 times 7, which I know that denominator reduces to just 7. That is a final answer. I cannot take the square root of 35 nicely, and I don't have a denominator with a radical expression. So in the next example, what would you multiply both the numerator and denominator by so that we can have a denominator with without a radical expression? Multiply it by the square root of 8 over the square root of 8. That is going to give you the square root of 16 in the numerator and 8 in the denominator. However, I can go further. I can take the square root of 16 to get 4 over 8 and continue to simplify, and there is my final answer. Now looking at the next one, what can we do? Well, we can split this as the square root of 72 over the square root of 3, and then rationalize the denominator by multiplying both the numerator and denominator by the square root of 3. And then I would get, well, I could actually look at that square root of 72 and say, hey, I know the square root of 72 is, I can simplify that. 36 times 2 times the square root of 3 over 3. And then I could take square root of 36 is 6 times the square root of 2, still times the square root of 3 over 3. Now I can simplify. 3 goes into 3 once, 3 goes into 6 2 times, giving me 2 times the square root of, combine those two, 6. Now, looking at the next one, I have a binomial in the numerator, a binomial in the denominator. So I got to be clever when figuring out how I'm going to rationalize that denominator. I have to be very clever. Well, I know these are binomials. So I know I'm going to have to multiply by something. If I multiply And again, I'm trying to rationalize the denominator so I don't have a radical expression in the denominator. If I multiply by the square root of 7 plus 3 in both the numerator and the denominator, well, I'm going to have to FOIL the numerator. First, outer, inner, and last. And in the denominator, look at what beautiful thing happens here. Square root of 7 times the square root of 7. 7. Outer, inner, last. And notice what happens here. Those are opposites, so they go away. So this is going to give me, well, let's see. Oh, I can't combine any of those. That looks messy, but, you know, I'll deal with it. But I can simplify the denominator. So that would be my final answer. Doesn't look like a final answer, but it is. Now, how did I decide what to multiply both the numerator and denominator by to rationalize the denominator? Well, notice I kept this term, but I changed the operation connecting them. So square root of 7 plus 3 and the square root of 7 minus 3 are what's known as conjugates. And conjugates, when you multiply them together, always gives you the difference of two squares. So if I were to FOIL conjugates, a plus b and a minus b, those are conjugate pairs. I'm going to get a squared plus ab minus ab gone, minus b squared. The difference of two squares, no radical expressions when one of your terms in the original binomial is a radical expression. So, we've talked about like terms, we've talked about combining like terms. What happens if those terms contain radical expressions? How do we know if radical expressions are like? Well, for us to combine those terms, for them to be like, for us to add or subtract, the root index and the radicand have to be the same. If the radicand or the root index are not the same, they are not like terms. So, can I combine these terms? Yes. I have 7 of these square roots of 2. I add 5 more of these square roots of 2. So that is just 7 plus 5 of these square roots of 2, which gives me 12 square roots of 2. And I don't need to see that root index. What about these? Are these like terms? Yes, they are. So 6 of them minus 2 of them gives me 4 of these square roots of 3. So let me ask you this. If I had 2 times the square root of 3 plus 4 times the square root of 5, can I combine those? Are those like terms? Not like terms. So that's as far as you could go on that one. So be careful. So let's try a few examples. If I have 9 of these square roots of 3 plus 7 of these square roots of 3, you should be able to get 16 of these square roots of 3. Oh, are these like terms? Can I get them to be like terms? Remember, I have to have the same radicand and root index to combine. So there's nothing I can do to that first term. However, that second term, I can simplify. I can simplify the square root of 20. I can factor the radicand, and I can get 2 times the square root of 5. Now I can combine those. And what am I going to get? 4 times the square root of 5. So sometimes you have to do a little work for them to become like terms for you to be able to combine them. Now, what if I have higher roots? And in this case, what if n is odd? Well, let's think about what this means. This is the fifth root, the root index is 5, of -3 times -3. I'm expanding that radicand. Now, in this case, it's saying I need 5 of the same base factor for one of them to come out and the other one disappears. So what is that base factor? What is that going to simplify to? -3. Now, could I have taken this and rewritten this with a rational exponent? Yes, -3 to the 5th power raised to the 1/5 power is -3 to the 5/5 power, which is -3 to the 1st power, which is -3. So no matter how you look at it, I could have expanded the radicand, or I could have rewritten this radical expression with a rational exponent and gotten the same answer. However, if n is even, that works if n is odd. If n is even, we need to think about the absolute value of a. The absolute value of a. Remember, why do we have to look at absolute value? Because if we have a negative number raised to an even power, that becomes even. So what should this equal? The absolute value of that radicand, which is 3. So be careful. Be very careful. Now, we've talked about what happens if we have a rational exponent, how to rewrite that as a radical expression. More importantly, with either having the exponent inside or outside of the parentheses. So let's talk about these examples and what we would get if we were to simplify them. The first thing I want you to do is I want you to take this expression with a rational exponent and write it as a radical expression. Well, the radicand is 121. The root index is 2. And again, if the root index is 2, I don't need to see it. And the exponent, whether it's on the inside or the outside, is 3. So I could write it that way. I could also omit that root index because it's 2. Now, do you want to take 121 and cube it? And then take the square root? Or wouldn't you rather take the square root of 121 and then cube it? If you know that 121 is a perfect square, you definitely want to do that and just cube 11. So if you know your rules, your properties, it makes these problems a little bit easier, saves you a little bit of work. Now, how do we address a negative exponent? Well, it's going to be, in this case, 1 over 16 to the 5/2 power. Remember, you can get rid of the negative in the rational exponent, the negative exponent, by keeping the base and the numerical value for your exponent, bringing it down to the denominator and dropping that minus sign. Now I'm going to have to go do a little bit of work. I'm going to take the square root of 16 to the 5th power. However, I don't want to raise 16 to the 5th power and then square root it. No, I would rather take the square root of 16 and raise that to the 5th power. Less room for error working with smaller numbers. But it's your call.